Okay. So, so first thing, I think the TA has just returned you the midterm. Okay. Yeah, the TA didn't grade it on your midterm, okay, exam, but the TA actually put the grade and the comments on a spreadsheet, okay, which has been posted to the EE class. Is that right? Yeah. So when you receive your exam back, okay, if you have any question about grading, please, go talk to the TA, okay, and in case if someone, who takes this class and he's not here, okay, today. I would prefer, okay, you inform that student to have him pick it up, okay, pick up his own midterm himself, okay, and to deal with his grading himself, okay, his midterm himself, okay. So yeah, I remember there's a duration, right? A deadline. Before that, you can go talk to the TA for any grading that you have problem with. Okay. What's the deadline? When is the deadline? Huh? Or not? You guys haven't set it up yet. Okay. How about we just set it to be 1 week? Okay, 1 week, which will be today's what's the date today? The 27th, right? So next Wednesday, okay, will be the last date you can go talk to the TA for your midterm, okay? So next week is it the 3rd? Oh, May, okay, May 4th, okay. So, well, then I can only say May the 4th be with you, okay? Yeah, so, you can talk to a TA and maybe get some points back if you wish, okay? So, we have not finished the Dirichlet triangulation chapter last time. Okay, we only cover about like 2/3 of that chapter. Okay, so my plan today is to finish this chapter and cover another chapter. Okay, so of course I could do this. I expect myself to do this because that chapter is short. Okay, that additional chapter is short. Okay, that's about like higher dimensional convex hull. Okay, we'll talk about that later. Okay, so let's first finish this Dirichlet triangulation. So last week we talked about the algorithm. Okay, basically it's a randomized incremental algorithm. Okay, you start from a triangle. Okay, you actually add like 2 additional points to your point sets. Okay, along with the highest point in your point set. Okay, you call that P0. Okay, and you add the 2 additional point, one p negative 1, one is p negative 2, okay? So together, I mean, they form, they form a triangle. Where is it? They form a triangle to enclose all the points. Okay, we assume p negative 2, okay, is, you know, is above all the point and is, you know, all the way to the left, you know, far enough, okay, and the p negative 1 is below all the point, and it's all the way to far to the right, okay. So but the real location of them is never going to be an issue, okay? The reason is because, okay, sorry, this one, okay. We are going to treat the p negative 2 and p negative 1 symbolically, okay. You could, you know, imagine like you know, without properly like picked the right p negative 1, p negative 2. I mean, it's just impossible to enclose all the points in that first triangle, right? So, but how to pick up the p negative 1 and p negative 2? I mean, you know, may be puzzling, okay? It's just not very easy. So I mean, instead of really calculating those 2 points, we never actually calculate them, okay? We just treat them symbolically, okay? So before we you know, talk about p negative 1, p negative 2, okay? One thing we need to know, okay, which will be used, okay, during the search for the location of the point, okay, because remember, like we also talk about this thing, right? This is a certain search structure that which basically like you need to be able to do certain comparison in order to find like you know, where the newly inserted point, like which triangle, okay, which diagonal triangle include that point in the center, or like use that, I mean, has that point, okay, has that newly inserted point on the edge of the triangle, okay. So basically, like you need to be able to do like a certain comparison. So in order to do the comparison, I mean, we need to, you know, define, I mean, the lexicographic relationship between points, okay. So given 2 points, P and Q, okay, let's say P is XPYP, Q is XQYQ, okay. We say, okay, you know, P is higher than Q, okay, if either YP is greater than YQ, okay, if that's the case, then P is higher than Q, or YP and YQ are the same, but XQ is greater than XP, okay. So in some sense, this is like for the second rule, okay, they sort of put like okay, if this is P, this is Q, if they are my drawing is it's not very well, okay, if they have the same y coordinate value, and the Q happen to have a higher larger x value, x coordinate value, then according to this rule, okay, then we say P is actually higher. P is actually higher. So in some sense, you can sort of like imagine, you sort of tilt this horizontal line a little bit, what should I say, like downward, okay, to the right. Okay, downward to the right. Okay. So this is like the lexicographic relation between the points. Okay, after we define that, okay, okay, so conceptually, okay, with that L -1, okay, to be a horizontal line lying below all the points set P, okay, and the L -2 be a horizontal line lying above the point set P, and we choose P -1 on L -1, okay, sufficiently far to the right, and the P -2 on L -2 sufficiently far to the left. But this is just a concept. I mean, really, like in reality, we don't need to really deal with the real location of P -1 and the P -2. Okay, I mean, but okay, one thing you need to know is that, okay, after you because it's a incremental algorithm, right? So you need to know at a certain point of time, okay, after you finishing, say, inserting R points, okay, what does the Dirichlet triangulation look like? Okay, what does the Dirichlet triangulation look like? I mean, including the P0, P -1, and the P -2. Okay, including these 3 points, what does the Dirichlet triangulation look like? Okay, so the Dirichlet triangulation of P, union P -1 and P -2 consists of the Dirichlet triangulation of P, point set P, okay, obviously, okay, as well as edges connecting P -1 to every point on the right convex hull of P. Okay, so this is like something like let me see. Okay, so this looks good enough. Say, so you have a couple points, right? Let's say the point say looks like something like this. Okay. I mean, I'm just give a random selection of points. Okay, and remember. Let me just for simplicity, let me just draw it something like this. So this is our P0, remember? Okay, this is our P0. And let's not connecting them. Okay, let's only connect like the lower part, because I want to show you guys the lower part is the Dirichlet triangulation. I mean, the boundary is the Dirichlet triangulation. And we have This is P negative 1. This is P negative 2, right? So, basically, okay, we will have the Dirichlet triangulation of the points of set P. Okay, so you can imagine, okay, you have some, convex hole, and then if the two cells share the edge, you draw a line between them. So you'll form certain triangulations, something like this. Oops, my drawing is very poor. Okay, allow me. Okay, something like this. Maybe it's a little bit too complicated. Okay, but other than that, okay, we will have edges connecting P negative 1 to every point on the right of convex hole of P. Oh, sorry. Did I make a mistake? This is P negative 1. This is P negative 2. I made a mistake here. Sorry. So for all the points, okay, it is going to connect to the P negative 1. And all the points on the right of convex hole, okay, will also be connecting to the on the left, okay, will be connecting to P negative 2. So that's terrible. Joy. You could imagine, okay, the highest and the lowest. The highest one is P0, right? The highest one is P0. We already know that, okay? But including the highest one, the lowest one, because they will be considered, on both sides of the convex hole, right? So the lowest point of P and the highest point P0 of P are connecting to both P negative 1 and P negative 2, as well as we have the P negative 2 and P negative 1. Okay, there's a edge connecting P negative 2 and P negative 1. So that's, after you insert, say, R points, and you finish the construction of the Dirichlet triangulation with P0, P negative 1, and the P negative 2. This is how it looks like. Okay, the reason for it to look like that is because, okay, we are treating P negative 1, P negative 2 symbolically. Okay, so how do we treat them? First, during the point location step, okay, when you are using this data structure to search for which triangle include the inserted point, okay? Okay, the following statements are basically equivalent. Okay, so now assuming we are inserting PR, okay, PR. and determine a position of a point of Pj, okay, Pj with respect to the oriented line from Pi to Pk. Okay, so because you can see, remember I told you, okay, every time you we do a H flip, okay, I mean the parent nodes are not deleted, right? So we will keep that age information in the parent node, okay, because like when we do a query, okay, we need to know like it is, which triangle it belongs to, right? Okay, so but this means like okay, eventually, when we do a query from the root to the bottom, okay, what we really compare with will be the location of the inserted point and the line segment stored in the internal nodes, right? So this is like what we need to compare with, like whether or not this point is like the relationship between the point and the line segment is on the left side or on the right side, something like that. Okay, so okay, these three statements will be equivalent. Okay, so first, Pj lies to the left of the line from Pi to P negative 1. So if this if the internal nodes store this line segment from Pi to P negative 1, see this P negative 1, we will treat it symbolically, right? So we are not really going to compute it. So we just, okay, when we see it's from one node, from one point to P negative 1, okay, then we immediately know that, okay, doesn't matter what where the new inserting point is, okay, it lies to the left of the line from Pi to the P negative 1. Okay, and then the second possibility is Pj lies to the left of the line from P negative 2 to Pi. Okay, so by the way, here, okay, if you read this one, carefully, okay, the line segment actually has an orientation. Okay, so for example, when I say Pj lies to the left of the line from Pi to P negative 1, what should I say? Like, if you reverse the order, then it is always to the right. Okay, same thing. Okay, it's from P negative 2 to Pi. Then if you reverse this order, then Pj will always lie to the right of the line from Pi to P negative 2. Okay, so this is like the way the segment is stored. Okay, there's like there's a ordered. Okay, the two ends are ordered. Okay, there's a certain meaning for this order. Okay, and or Pj is lexicographically larger than Pi. Okay, remember, when we say lexicographically larger than Pi, we mean Pj is higher than Pi, right? So we are doing that comparison. Okay, so these three statements are equivalent. So by saying these three statements are equivalent, we never need to compute P negative 1, P negative 2. Okay, as long as like the segment, okay, store in the internal node, okay, contain either P negative 1 or P negative 2. You know how to deal with this search. Okay. And then, okay, how do we check the illegal age? Okay, when the either p-1 or p-2 involve with the edge. Okay, so after the insertion, remember, I mean, we need to check if edge need to be flipped, right? To be exact, okay, what happens is that, okay, we are going to, when this new point is inserted, the original triangle, okay, is going to be broken into 3 smaller triangles, and each of them, okay, the outer edge will be considered to be flipped or not, right? We talk about this, and we need to do this like, maybe several times, right? Okay, as for how many times, we will do the analysis shortly, okay? So during the edge flip, remember, okay, we need to check if a point, okay, for example, say after this insertion, we have these 3 triangles, then we need to find the circle that goes through these 3 points and see if the other side of the point, this one, falls inside the circle or not, right? If it's inside the circle, we do the edge flip. If not, then we stop, right? We talked about this last time, right? Last week. So that computation, okay, if all the points, okay, if this edge as well as these 2 points do not involve p-1 and p-2, then obviously we could just do it the computation directly, right? Okay, because nothing needs to be done symbolically. Okay. This is the second step. Okay. So first, let me clarify this. Okay. Here we are checking PIPJ. This line segment need to be flipped or not. Okay. We are checking this line segment need to be flipped or not. And of course, like this line for this line segment, okay, it is like a shared edge by 2 corresponding triangle, right? Okay, and we could assume the other 2 vertices for the shared triangles. Okay, so this is PIPJ, and okay, it must be shared by 2 triangles. We assume this one is PK and PL. Okay. So we check if PIPJ need to be flipped. Of course, if it needs to be flipped, then the resulting edge is going to be, PKPL, right? Okay, obviously. Okay, so if the index IJKL are all non-negative, when I say non-negative, which include 0, okay, include 0, because remember P0 is also a valid point, right? Okay, so if IJKL are all non-negative, then it's a normal case, okay? So we don't need to worry about symbolic representation of any point. So we just treat them, normally, okay? In other words, we are doing just like the regular, edge flip process. Okay, but okay, say if PIPJ is an edge of the triangle P0, P-1, P-2. Okay, so these edges are always legal. Okay, these edges are always legal. So when you consider, okay, for example, I mean, you may wonder how come we have we still have the edge P-1 to P-2, this edge. Because obviously when you insert the point, okay, this is a first edge that, I mean, the first few edge that should be considered to be flipped or not, right? Okay, because, well, okay, think about it. When you first insert one point, okay, then it's going to break this large triangle into three sub-triangles, right? So you need to consider, okay, you know, the outside, you know, edges, right? And you will be surprised to find that, okay, I mean, you don't need to flip any edge when the first point was inserted. Okay, that is the reason you can see that not only P-1, P-2 stays, but also P-2 to P0 and P0 to P-1. These three edges are, you know, actually there at the beginning, right? And they will stay. They will always stay. They will always stay. It is because of the rule, okay? The rule we just mentioned, okay? And you can see that we never need to do any computation, okay? As long as PIPJ is one of the edge, either P-1, P-2, or P0, P-1, or P0, P-2, any of these three edges, then, you know, nothing need to be, you know, done. We just okay, consider it is legal edge, and that's it. Okay. The last one is a little bit okay. All other cases, okay, in this situation, okay, PIPJ is legal if and only if the minimum index of KL is smaller than the minimum index of IJ. Again, this computation does not require you to do the exact like a original edge flip computation to find if the fourth point needs to be in the circle or not. No. You just check the index. Okay. So why do we do that? Think about this. Okay. What would be the cases that we consider here? Okay. You will find that at most one of the indices, IJ, is negative, right? At most one of them is negative. Why? Because if both of them are negative, we already consider that in the first situation, right? That's P-1, P-2, right? We already consider that in the first statement, right? So, for IJ, for indexes I and J, they can, at most one of them can be negative, okay? And, for another reason, K and L, at most one of them can be negative. Why? This one may not be so obvious. It is because, okay, the reason we are considering H flip, the reason we are considering H flip is because of the insertion, right? Okay, and when you are doing insertion, when do you need to consider H flip? Okay, let me show you the picture again. Yeah, here. When you insert a point, you will consider this edge and this edge and this edge, whether or not they need to be flipped, right? So think about this. Okay, no matter you are talking about this edge or this edge or this edge, okay. I mean, for example, let's take this one as one of them. Okay, for this edge, okay. I mean, this vertex and this vertex will be the PK and the PL, right? In our discussion here, right? These 2 points will be PK and PL. This edge will be PI, PJ, right? So, I mean, you will find that, okay, these two will be PK and PL, right? So, PK and PL, one of them has to be the point that just got inserted. Okay? Let me show you again. Okay, so when you consider this edge, okay, remember I told you, okay, for PIPJ, when you consider flip, okay, we will treat the other two vertex of the shared triangles as PK and PL, right? So for this one, okay, obviously this is PR, and there's another one here, right? So you can see PR, the newly inserted point, also will be one of the PK and the PL, right? Okay, same thing goes for this edge. Okay, and you may ask, how about if we continue doing this? Okay, so after the flip, it becomes this one, right? And the edge we need to consider flipping, okay, again, will be this one, right? So you can see that, okay, for this edge, let's say, now we treat this one as PIPJ, and the other two vertices that we consider, again, you see, the PR is one of the PKPL, right? This is PR, right? This was the point that we just inserted, right? Okay, so we need to, here we flip again, okay, we flip again. But, I mean, what I want you to know is that, okay, because PK and the PL, you know, one of them will be the newly inserted point, okay, and in our algorithm, okay, we start by inserting, the first point we insert is what? Actually P1, right? Actually, the first inserted point is P1. I mean, we start from the triangle P-2, P-1, and the P0, right? And obviously, I mean, we don't do insertion when we construct that triangle, the initial triangle. And the first point we insert is P1, okay? So since one of PK or PL, okay, one of them is the newly inserted point. So, I mean, as I say, that their index, okay, one of the index has to be greater than, well, not only non-negative, but also at least greater than 0, right? Okay, so that's, so that's why, okay, we say at most one of the index K and L is negative. At most one of them is negative. Okay, it's impossible for both of them to be negative because we never insert a negative point. Okay, a point with negative index. Okay, we never do that. Okay, and then this restrict a lot of things. Okay, so basically like here you just check like you can summarize a lot of conditions in here. Okay, you can summarize a lot of conditions here. I mean, obviously, okay, in this statement, in this case, IJKL, at least one of them is negative, right? Although they are, I mean, we know like IJ, one of them, at most one of them is negative, and at most one, I mean, at most like one of KL is negative, but we know at least one of IJKL is negative. If all of them are not negative, again, we have dealt with that in the second statement, right? We would have used the regular H flipped already, right? Okay, so the first one is to deal with the edge involved, like the first three edges. So we treat them symbolically. For this one, okay, it also deals with the edge that involve either P negative 1 or P negative 2. It's just, now we, as I say, like, okay, if only one of them, only one of PI, PJ, PK, PL is negative, then whichever is negative, okay, for example, okay, if KL, one of them is negative, okay, that means, for example, it's the case like, well, again, I forgot to point this. Consider this. Consider this one. The I and the J, this is PI, this is PJ. This is PK, this is PL, right? Okay, look at here. Let me maybe use, let me try to mark it. This particular edge, let's consider the two ends of this edge to be PI, PJ. Okay, and the other two vertices will be, this one is PK, this one is PL, right? This one is PL, right? And you can see the minimum of PKPL obviously is smaller than this PIPJ, right? So we need to keep this one. That's the reason this one is kept. Obviously, if it's the other situation, okay, then we need to flip, okay, which also create one edge in the convex hull of all the points. If originally it's like that, we flipped it, then it create one of the edge in the convex hull. Okay, that's the first. The second thing, the second case is that, okay, IJ has one negative edge, negative index. KL has one negative index. Okay, IJ has one negative index. KL also has one negative index. This is a little bit special. Okay. What should I? P negative 2. Okay. Sorry. I need the last one is This one is not good either. How about this? Ah. Okay. So let's consider an initial case. P0. This is P negative 2, right? This is P negative 1. Okay. Let's see. Is it possible? Let me see. The first point insert. The first point after the insertion of the first point. This is P1. P1. It doesn't matter where the P1 is, okay? That all these edges are legal, so nothing will be flipped, as I mentioned in the first statement, okay? Yeah, I don't think it's possible to have, I mean, both of them to have like one negative index. Anybody? Which one? Vertex at where?
An arbitrary vertex and p minus 2 of pi pj.
Say it again.
Just pick an arbitrary point and p minus 2 of pi and pj.
P negative 2 and pi pj. You mean like an obvious arbitrary point?
Sorry, not arbitrary. The bottommost point.
Oh, the bottommost point. Let me see.
P is pi and the p minus 2 is pj. And you can see p minus 1 is pk or pk.
Oh yeah. Okay, it makes sense.
Is on the top.
Yeah. Okay, so this is on the top or and at the bottom. Yeah. That's the only case. Okay, so in this case, I mean, the edge to be considered is this one. Okay, so this is pi pj, and we have one vertex here, and the other vertex is here. Okay, this one. Okay, so you can see that. Okay, let me see. In this case, you can see this is PKPL, right? So the minimum of PKPL is negative 2. The minimum of PIPJ is negative 1. So yes, it's subsum the situation that we should keep this edge, right? It's subsum the situation we should keep this edge. And if it's the other way around, like we have edge, we have dotted edge, like this, then this edge would have been flipped, right? Because this edge, okay, this edge, you treat this one as PIPJ, then the minimum of PIPJ will be P negative 2. And the corresponding like two vertices will be P negative 1 and something. So the minimum of these two index of these two vertices will be P negative 1. So this one is not satisfied. Yeah, good. Thank you for pointing that out. So basically, you can see that, okay, we are able to deal with all these symbolically, okay, without having, you know, in case when the P-1, P-2 are, you know, involved, we don't need to, you know, really calculate the edge flip. Okay. So, well, let's take it's already 10 o'clock, so let's take a 10 minutes break. When we come back, we are going to discuss the complexity of this algorithm. Okay.